It's not a phase, Mom. It's who I am. I'm going slightly insane. Okay, so last time we were here, we took a look at this Coulomb's law example problem for electrostatics, where we had point charges A, B, and C. And we found that by taking a look at the forces and adding them together as vectors, we had a force value of 156 newtons. What we're going to do here is we're going to take the exact same charges at the exact same distances, but we're going to rearrange them, okay? So the way we're going to have this looking now for us is we're going to have charges A, B, and C, but they're going to be set up so that charge A is going to be up here. We're going to call this charge A. Charge C is going to be down here, C, and we're going to have charge B over here, okay? And this is definitely not to scale, but I'm doing my best. What we're going to find here is that with the distances being the same, this distance here is going to be 0.05 meters, and this distance here is going to be 0.04 meters. And if you've been following along with your math courses over the years, you clearly see that this doesn't make any sense, because this side right here will be, drum roll, well, the drums are a little silent today, but it's 0.03 meters, because this is now just a 3, 4, 5 triangle. That also allows us to say, well, now that I've said this is a right angle, it also gives us the values of angles here, if you know your triangles at all. We know that, and I'll do this in a green color, this angle here is approximately 53 degrees, and the angle up here is approximately 37 degrees. Okay, so that's the triangle we're going to set up. Because of this, though, if we do what we did in our last example and we take a look at what are the direction these forces are acting, and we're once again going to concern ourselves with just charge A, what we can see here is that charge A is going to be attracted to charge B. This is the force on charge A due to B, and we saw last time we were here that this has a value of about 72 newtons. If you want to see how we get that, check back in the last video on how we use Coulomb's law. We also know that the AC charge is going to push away, oops, kind of moving to the other one. This is the force on charge A from C, and it has a value of 84 newtons here. So we still have the same force amounts, 72 and 84, but we can no longer just add these together. It is very clear from this diagram that these are not acting in the same direction. In fact, they're acting in not just two directions, but in two dimensions of directions. Things are no longer just on an x-axis with left-right, and they're no longer on a y-axis just up-down. They are on the xy plane. And because of this, we're going to be forced into using a little bit of SohCahToa to solve this out. So if we actually want to find what the net force is on charge A, we've got a little bit of work to do for ourselves here. Okay. The first thing we could recognize, and this will make our life just easier as we go along, is it's important to recognize that the blue force here, the force on charge A from C, that 84 newtons, it is technically on an axis here. If we redraw charge A and we give it a quick little axis, ooh, can I do this? Is this going to be nice? Quick little axis. Can I change the color of it? Not exactly. So there's the axis of charge A. This 84 newtons is on the y-axis. It is pointing straight up. Okay? The issue we have here is actually with the 72 newtons. It is being pulled down this way. Not drawn to scale, but drawn for clarity. Now, what we can see here from either diagram, and if we kind of look at the triangle, it's a little easier to see. We know that if I drew my axis back in, we know what this angle underneath is. We know right here that this angle underneath, that is 37 degrees due to the triangle we had before. It also lets us know that the angle we have up here, that is 53 degrees. Because of this, the SohCahToa that you would like to use is entirely up to you. If you would like to use this 37 degrees here in the bottom, that's fine. If you want to use the 53 degrees here in the top, that is fine. What is important is that when you are solving for the components of this force vector, that is the x components and the y components, or the y components and the x components, you are using the proper sine, cosine, tangent terms, whatever you're using, okay? If we look at our 53 degrees, our orange angle above, we need to note that our y-axis is the opposite side and our x-axis is the adjacent side. If we did the same thing for our 37 degrees, we would actually see that our opposite side is the x vector and our adjacent side is the y vector. So it doesn't really matter which one you use, but you have to recognize that given your triangle, you may have to use sine or cosine to find the x vector, and sine and cosine to find the y vector. Okay, so just be careful about that depending on what you're using. What we're going to use in this problem is I'm actually going to use the upper triangle, the 53, so we're going to stick with the orange here. If you'd like to double check my work and use the green one and set up similar triangles and similar sines, cosines, be more than welcome to do that. You'll get the same answer, you get the same result, it's totally awesome, but we're going to stick with the orange here for now. Okay? So what we need to do here is, since we know that this hypotenuse has the length of 72 newtons, we need to just break it up and figure out how much force is in the x-axis and how much force is in the y-axis. So to do this, and knowing that this is the hypotenuse here, that long pink line, what we can say is for each of these, and let's do this in a different color, let's do this in purple. We can say that the force on charge A from charge B in the x direction, and I'll say x hat direction. I would just say the x direction. We haven't really covered x hat. So just in the x direction is going to be equal to 72, my hypotenuse, times the cosine of 53 degrees. And the way I got that is I know that the cosine of some angle is equal to an adjacent over a hypotenuse. That goes all the way back to the classics of SohCahToa, where this is the cosine equals an adjacent over a hypotenuse. So cosine of an angle equals the adjacent over hypotenuse. I move that hypotenuse over, so I get 72 times the cosine of 53 equals the adjacent side, which is the force of AB in the x direction. That is this value up here. F of x, or fx, excuse me. Okay, so this will give us a value here of, what is this number? 43 newtons. And that value is acting in the left direction. Look how we drew this here. This is acting in the left direction here. It's going to the negative x direction, okay? I haven't put any negatives in because I'm saying it's moving to the left. If we want to do the same thing, but for the y direction, well, the force of AB in the y direction, we're not using cosine this time, we're going to use sine. So if we take a look at sine for SohCahToa, sine of some angle is equal to opposite over hypotenuse. Moving the hypotenuse over, we quickly see that this is going to equal 72 times the sine of 53 degrees. And technically there are newtons on that 72, and that's how we get our unit at the end. Sine of an angle and cosine of an angle are unitless quantities. It's a function being used there. But this gives us 58 newtons here, and it is pointing down. Okay? So now I have everything broken up in either up-down directions, because the 84 up here, or the 85, yeah, the 84 up here was up, the 58 is down, so we're up-down, we're on the y-axis, or we're left-right. We don't have anything acting to the right, but we've got 43 newtons acting to the left. So what we'll do here is we will sum our forces in each direction. We'll sum the forces in the x direction, and then we'll sum all of the forces in the y direction. Okay? When we do this, we need to pick what direction we'd like to be positive, what direction we'd like to be negative. It doesn't matter what choice you make, but as soon as you make that choice, you need to stick to it for the rest of the problem. Let's just make up positive and down negative here. Because we only have one force in the x-axis, let's just make our life easy and make left positive and the right negative. So the sum of the x's is just 43. It's positive even though it's left because we said left is positive. 43 newtons. That's it. There wasn't any other forces there, nothing else to add. In our y direction, though, we have two forces. We've got the 84 newtons going up, so it's positive. And then we're adding to that the 58 newtons going down. Since it's down, it's technically a negative, so minus 58 newtons. 84 minus 58, what's that give us? 26? 26 newtons. And since this is a positive number, we know this is acting up, and then this is acting to the left here. Okay? So those are two directions of net forces there for the x and y directions. If we then want to find what the total net force is, we got to do another step. This is charge A. We know now that in terms of net forces, there is only 26 newtons going up and 43 newtons acting to the left. Well, how do we add these two forces together in order to get a net resultant force? Well, since they're both vectors, we need to add them with the head-tail method. So we could either slide the 26 over to the left, so it pops up here, because now we have a nice head-tail method right there. Or we could take the 43 newtons and slide it up on the 26, put it here, so then we once again have a nice head-tail method acting right there. Okay? So either way, we have a head-tail method. Either way, this force goes from start to finish. Now, how do I find that long edge of either of these triangles? That is simply the hypotenuse. And if that's 26 and that's 43, it doesn't really matter which way you slice it. We can simply say that we've got three sides of a triangle here, A, B, and C. And now we're going back to Pythagoras. We can say that c squared is equal to a squared plus b squared, which means that c is equal to the square root. I don't care if you write a big radical. I'm going to write it like this. A squared plus b squared to the 1/2 power. Remember, taking something to a fractional power is the same as square rooting it. And then this just boils down to saying whatever 43 squared is plus 26 squared, and then take the square root of it. Make sure you're doing those order of operations in the correct order there. And when we finish that out, we should get something around 50 newtons. I think if you take it with sig figs, 50 newtons actually becomes our answer there. Okay, you might get something a little bit more. I just kind of did some rounding there. Okay, so that is actually the resultant vector of 50 newtons. And that is what the net force on A is due to everything else. Okay, due to both B and C charges, this is the net force acting on A when we have a kind of triangular setup. If you wanted to, you could figure out what direction this is pointing. You would simply use inverse functions here, inverse tangent, to figure out what this angle is. And then you would add that to 90, because remember, you always start from the positive x-axis and wrap that around. Okay, so if you wanted to, you could do that. We're not going to do that in this problem, but you could if you wanted to. Only other thing I'm going to talk about just real briefly is, while we kind of wrote this in a more polar notation here, because this is the 50 newtons and then this angle up here would be the direction it would be pointing, you could write this in other notations just to make your life easier. If you recall from last year, unit vector notation, unit vector, if you recall, is like I hat, j hat, and k hat for the x, y, and z directions. We could write this in unit vector notation as just saying that the force is equal to, in the x direction, we have 43 acting to the left, and left is traditionally negative, so we could just say like negative 43 I hat plus the j hat, which is 26. And then that would be 0k, so we wouldn't write anything there. Or if we wanted to write it in a slightly similar way, we could write it like this. We could say negative 43 comma 26. This is more of a calculus way of writing a vector notation. So that's one way to do it. In regards to this z hat being the third axis, if you're throwing up physics gang signs, if you did want to run a Pythagorean theorem for 3 dimensions, you can. It's very straightforward. All you do is instead of saying c squared equals a squared plus b squared, it is simply d squared equals a squared plus b squared plus c squared. This is a 3D Pythag. It's a 3D Pythagorean theorem. It'll still get you what you want there. Okay, so nothing's really changed in that regard. So this problem's kind of similar to what we did before, except this time, because we have a kind of weird geometric setup with a triangle, we are stuck using sine and cosine. It did make the problem much, much longer because we had to break things up and then make sure we were adding things and subtracting things in the proper direction based on the drawings we drew. But in the end, it wasn't any math you didn't know how to do. It's just you need to be very careful as you're walking through it for these type of problems. Okay? If you've got any questions for that, hit me up. But for right now, we are finished. Take it easy. Adios.